and we'll go ahead and get started with our next presenter. We have Lang Yu, who's from Ohio State, presenting today on characterizing communication patterns in distributed LLM inference. Uh, the floor is yours, Lang.
Thank you, Galen. Let me share my screen real quick. All right, can everyone see it?
Looks great.
Sure. So, hey everyone, my name is Lin Xu, and I'm currently a upcoming fourth year PhD student at The Ohio State University. And in NowLab, I work on the HiDL project with Dr. Panda, where we explore efficient techniques to accelerate and deep learning workloads. Today, the topic will be characterizing communication patterns and distributed large language model inference. So let's get right into it. So it will follow a outline of a general introduction, the motivations, the problem statements that we need to cover, the analytical model that we derive in this paper, and some analysis and some metrics that we look through and the real world inference workloads, and then we'll reach the conclusions. So to cover a little bit about the background, inference is the hot topic right now compared to pre-training in the previous days. Inference is the process of using a pre-trained large language model to generate text or predict on the given input. If you give it a prompt, it will try to generate text out of it. So why does inference time steamed up? Why is it the hot topic right now? Because as you may know, that there are a lot of better models that came out recently I would say that in the recent months, such as DeepSeek R1, the Gemini 2.5 Pro, or OpenAI O3. These models are proved to be really capable in reasoning and decision making and coding, and they all utilizes advanced reinforcement learning algorithms like GRPO or DPO, in PPO, you name it. Generally, scaling inference line compute allows a bigger playground for all of these techniques to come together. And complex large language models capabilities apparently emerges with computation resources allocated to inference. So if we look at inference, it has some similar challenges towards when we compare it to pre-training. If you have a really big pre-trained model, if you want to deploy it, there's going to be multi-GPU, multi-host deployment. And when we deploy this model across GPUs, among workers, among nodes, communication will definitely comes to the picture on the overhead. How many overhead is it bringing into the picture? Another thing about inference, which is really different from training, is that it has separate prefill decode stages, which is compute bound for prefill stages, where we just process a batch of the full prompt into all the workers, and the decode stages where we have tokens after tokens. The model will get warmed up and trying to spit out the actual answers that we care about. This is kind of unique communication pattern and it's different from pre-training. And there's a lot of when it comes to measuring the performance of inference for pre-training, we know that we have model flops utilizations and the flops per GPU, but for inference, it is more attached to real-world application. It is really attached to how user experience the whole service. So the latency, the time to first token, the time per output token is definitely important, and all these metrics are grouped into a category called service level objectives. So next, I'm gonna present some of the problem statements that we are hoping to cover in this paper. So what are the predominant types, volumes, and patterns of communication during multi-workers, multi-host inference? Can we develop a analytical model given a certain framework to predict such communication volumes with certain parameters, certain frameworks like parallelism degrees, model architecture, and such. And what are the impact of these communication patterns coming along with also the speed up in computations? What is the impact of these factors that place together when it comes to SLOs, service level objectives? And given a set of resources, what are the comparative impacts of different parallelism layout towards the communication volume and towards also the actual experience that we have in our real use case? So let's get into the pretty technical part where we actually look at some variables and we try to derive the actual formula for the communication volume, the analytical model parts. So some words ahead. There, we are going to model the communication volume across different parallelism layout. We'll be covering tensor, pipeline, and eventually combine them together, the hybrid parallelism. These formulas and also the mechanisms are really seek through VLM frameworks and the VLM framework, and it is also conducted on dense transformer architectures with llama-based architectures. So we'll be mainly focusing on the hidden dimension size, the number of transformer layers, and the model, the bytes per element, the prefill sequence length, the length of the prompt that you give to a user before you can try to get its answer, the tensor parallel size, the pipeline parallel size, the vocabulary size, and also the decode sequence length. So let's jump right into tensor parallelism. So to give a little bit of background, tensor parallelism is actually, in short words, it's a distributed matrix multiplications mechanism across the GPUs. It is first introduced by Megatron LLM during the pre-training era. So if you look at the right figure, this is a figure in the Megatron paper. This is actually a figure of pre-training. So for each transformer block, there will be two reduced for and backward for tension output projection. There will be two reduced for MLP down projections. And for inference, we don't only care about forward pass. So we'll cut that by half. There will be a total of two reduces at the message size of 10 dimension size elements during each transformer block during inference. So there's a VLM framework when you are actually before doing the inference, there will be also another one reduced at the embedding layer per token. And finally, you want to gather the lodges from all the tensor parallel workers. There will be one gather at the end per generated token. So if we look at the communication volume here, there will be consisted of two parts. One is the reduced part, one is the gather part. So the first part, we will also be covering an additional reduce at the embedding layer per token, and then we'll have two reduces per transformer block, and we'll be timing multiplying it by the total sequence length, prefill sequence length, and the decode length -1 because we're already spinning out one token after the prefill stage, and then we'll time it up by adding the hidden dimension size factor, the bytes per element factor. For bflow 16, there will be 2. For FP16, there will be 2. For the full precision FP32, that will be 4 bytes per element. And then we will times a correctional factor, which is in the nickel test performance documents to obtain the to adjust for the bus bandwidth. So if you can look in the down left, this is the volume, actual volume for if you're doing pure tensor parallelisms using VLM framework for inference. Next we'll look at the pure pipeline parallelism. So if the pipeline parallelism actually places a subset of the transformer layers among the GPUs. It will pass the activations using point-to-point send and receive between the pipeline stages. So each pipeline stage will forward 2 times the sequence of the sequence length of prefill times the hidden size times the number of bytes per element. Why a factor of 2 here? Because it needs to pass along the K activations and also the V activations. In VLM, it will be a separate 2 send and receives. For decode, for each token, that will be 2 times H times the small case B bytes per generated token. So the actual communication volume is heavily dependent on the number of links with this type of deployment. The first pipeline rank will receive no input, and the last pipeline rank will produce no intermediate tensors. So if we look at the volume of pipeline parallelism, it will be just the number of links times K and V times the actual prefill stage sequence length, and then the decode sequence token number of tokens times the hidden size times the bytes per element. So if we are taking hybrid parallelism into the picture and we're combining tensor and pipeline parallelism, things are getting to get more complicated because there will need to be some additional factors and communication incurred with this setup. So for the first pipeline rank, we have, and as usual, we have an additional embedding or reduced volume. For the following stages, we characterize this volume into 4 stages. One is the all-reduce, which is typically from the tensor parallel group. One is the all-gather. The all-gather here is usually used between pipeline stages. So if you have 2 GPUs doing tensor parallel in the first pipeline stages, when it is sending the activations, the tensors to the next pipeline stage, we need to rematerialize the tensors when it hits the next pipeline group before it does the splitting for the next tensor group. So there will be additional all gather. And then the third part is the gather volume. The fourth part will be the pointing point volume when it comes to pipeline parallelism. And also the all reduced volume here will be reduced by the factor of P for pipeline parallel. This is also some factors here. It will get the communication volume will get mediated by the actual additional groups that it splits upon. So actually, hyperparallelism has some additional communication volume characteristics that we care about. So let's quickly go through the analysis and performance characterizations that we did. So experimental setup, we conduct our studies on OSC kernel systems from 1 node to 2 nodes. It is a machine with a compute node configurations of 4 NVIDIA H100s per node connected with NVLink. And for the internode connection, it will be InfiniBand NDR 400 gigabits per second, and there will be 4 NICs per node, which is, I know it is a pretty fancy setup. For software packages, we are using PyTorch 2.6. We turned off the torch.compile. We allow eager executions, and this and we allow no custom all-reduce implementations both from PyTorch and from VLM. For VLM, we are using the 0.8.5 post-1 version with the V0 engine, which is pretty well matured at the moment. We know at that time we know that V1 engine is still in rapid prototyping, so we didn't use that. And the nickel version that comes with this setup is 2.21.5. The models we are going to cover is the Llama models 3.23 billion, which is the smallest, and then we gradually scale up 8 billion, 13 billion. These models all differ in hidden dimension size, the number of layers, the number of vocabulary size, and also the dense. They are also the same thing is that they are all dense models. The server configurations will be single request and batch size of 1, which allows typically no overlap of compute and communications. When it comes with compute and communication overlapping into a picture, things will get trickier. So we want to make things clear and read and probably allow more readability and understanding towards the readers. And for PyTorch profiling, we have PyTorch profilers, and we also retrieve our SLO metrics through VLM RESTful observability APIs. So if we look at the message sizes and frequency here for tensor parallelisms. As we increase the tensor parallelism size, we can see uh, there's a change. Actually, there's a change in the shape because we are splitting the matrix among more typical workers. And also, if we look at the prefill stage, take TP size of 2 as, for example, if we look at prefill stage and decode stage, you can see there's a large number of R reducers at decode stage. That is because we need to do R reduce at each token level, and it is not processing in the batch. There will also be a gather, which is just decode prefill the decode sequence length -1. And if we look at TP size, we scale up the TP size from 2 to 4, we can see that number of counts didn't change. If then we compare our message sizes and count across model sizes, so you can see if we scale up the model sizes, we have more transformer layers, more hidden dimension, a larger hidden dimension size. We have more counts. We have a larger message size that conducted using RReduce. So the RReduce frequency, it really depends on the transformer layers and decoding steps. The message size really depends on the sequence length and the hidden dimension. So if we look at pipeline parallelism, we tested 2 configurations which are both within the node, 2 pipeline sizes and 4 pipeline sizes. The only difference here is that we have more links when we do more pipeline parallelism. So if you look at the send and receive, for a pipeline size of 2, we have only 1 link. The count for prefill stage processing in a batch of the prompt, there will be only 2 send and receives, and 2 sends and 2 receives, which is K and V. And if we look at decode stage, it's pretty obvious that we can match it towards our formula. 254 divided by 2 is actually 127, which is just the decode sequence length -1. And if we scale up the pipeline size as we go from 1 data link to 3 pipeline links, the cost and the counts will actually times by 3. So another thing that we actually look at is we do TP hybrid parallelism within the node, which is 2 tensor parallel group and 2 pipeline parallel group. You can see here, compared to a TP of 4, we have less or reduced costs, and additionally we have a all gather and a send receive cost. So for pipeline parallelism, the frequency point-to-point send and receive communication really depends on the pipeline links. The pipeline message sizes will remain pretty small, and it really depends on the hidden dimension size. So the key takeaway here when we look at actual frequency and the message size of these metrics when we do these parallelism is that we are seeing for tensor parallel, hybrid, and pipeline, we have a really high frequency of moderate message sizes, not to tens of gigabytes of RReduce, just like in pre-training, we are still doing a small to moderate message sizes. And decode stage is more communication heavy, which is a lot of high burst, small message sizes communications happening in decode stage. And the RReduce and point-to-point are the major operations that we care about when doing these inference. So if we actually look at the communication volume when we are matching our formula here, the upper half is actually when we're doing communication volume analysis on a collection on different model sizes. You can see for pipeline size, for pipeline, it has a minimal communication overhead because it is only sending small hidden dimension sizes of 1 tokens. And for tensor parallel, it is really heavy because it also depends on the number of layers. For each layer, we have 2 reduces. And in between, it is the hybrid parallelism, which has moderate communication volume. So the key takeaway here is that tensor parallelism has the most communication overhead that scales with the model size and sequence length. Pipeline parallelism has the minimal pressure on network, which is good for bandwidth constraint and long sequence scenarios. However, it is actually underutilizing GPU compute. So in these scenarios, we are spinning tokens by tokens with no micro batching or communication overlap, computation overlap. So it is actually detrimental to the latency that we are experiencing. Hybrid parallelism strikes a balance between the communication overhead and the GPU utilizations. So we'll quickly go through the SL evaluations, that the measure that people actually care about: the time to first token, the time per output token, and end-to-end latency. The time to first token is actually a prime indicator of how well we are performing during the prefill stage, where it's timed at the start when you are inputting a prompt, and then the time that you're first getting your first output token. The time per output token is actually a mean over the decode stage. So we'll have the overall time spent during the decode stage, and then is calculated among the total output token during the decode stage. So for tensor parallelisms, we can see that as we scale up the tensor parallelism, the time to first tokens is actually keep decreasing because we are splitting the matrix modifications among more workers. Since prefill stage is actually compute bound, we are keep seeing the speed up. Even if we scale across the node, the speed up is beating the actual communication overhead. And when we look to the decode stage, which is more memory bound, one token by one token, scaling TP within a node still gives up a sense of improvement, but when it's scaled across the TP, scale across two nodes when we are using the internode connections, it is really skyrocketing as the teapot. So if we look at so this is also paired with the compute bound for the prefill stage and the memory bound for the decode stage. So if we look at pipeline parallelisms, which is pretty detrimental to I would say really sensitive to latency metrics. If we scale up the prefill stage uh, within a node to across the node, it is actually increasing time to first token because we are creating more links and more data dependencies. And as we scale up across more workers, more GPUs are getting idle during the prefill stage. For the decode stage, we are seeing still within nodes where everything is good with the NVLink Ultra, with the high bandwidth NVLink connection, and we scale up when we scale up across the node, with more links, more idling, the teapot will skyrocket. So the TTFT, with TTFT, we have data dependencies, and the latency will scale with the number of links. The PP, the final configurations of A workers across the node boundaries will get us the largest TTFT. And for teapot, which is memory bound, it is not favorable to pipeline parallelism. It is dominated by critical links across the node. So if we combine the hybrid parallelisms, if we combine pipeline and tensor parallelisms, we are seeing some really special metrics here. When we also coming from pure tensor or PP parallelisms, we are doing from a 3 billion model to a 13 billion model for hybrid. So given the time constraint, I'm just gonna present the takeaway here. So surprisingly, we are seeing a really good benefit of TP of 8 when we are doing a large language model, a larger model size during prefill stage, which is compute bound. And also this prefill stage speed up on computation is beating all the communication overhead. When it finally comes to the decode stage, TP8 also provides a better choice overall. And the pure pipeline parallelism has acceptable end-to-end latency and teapot. The one reason about it is because if we are also splitting stages, we are also splitting the model sizes across the ranks, we are also witnessing less computations per GPUs. So the execution time for each GPUs will also decrease as we scale up the PP size. TP4 and PP2 remains mostly unbalanced. So mainly because for hybrid parallelism, it has more small TP collectives. compared to pipeline parallelisms, and it also creates a dependency where there's only the one internal link between the pipeline stages, which is the lowest bandwidth in our configurations. And PP8 will wins with only one internal link. Although we have a really large amount of data dependency here, but given the actual speed up from the computations and much less communications over a long sequence of decoding stage, we are seeing PP wins in this case. So if we go through the conclusions, inference workloads impose communications with moderate message sizes, small to moderate message sizes, that as I can say, and they are high burst collectives. Decode stage dominates the communication frequency. If we look forward to optimize more on the communication side, I would suggest looking through RDUs and point-to-point. For tensor parallelism, it offers better GPU utilizations and computation efficiency, but it has a substantial communication overhead per layer. It fits really latency sensitive and short generation tasks. Pipeline parallelism offers a minimal communication overhead. If you have a lower spec machine, if you have lower bandwidth, you are constrained with internal communications. We suggest pipeline parallelism to fit more long generation tasks. And also the final note is that while computation parallelism can overcome communication overhead for short sequences, it diminishes with longer sequences and internal deployments. And I'm aware of that. There's recent attention towards the MOE models, which use expert parallelisms and another collectives like all-to-all, and we leave that to the future works. All right, and also this paper is on arXiv right now, and you guys can just do a single search on the Google and it will pop up in the arXiv. All right, I think that will be end of my talk, and thank you, everyone.
Lang, that was a great talk. We've got a few more minutes. Oh, they might have pulled you back already. So, if you have questions for Lang, please take a look at the Slack channel. Oh, there you are. And Lang, I think we have a few more minutes. The last talk is recorded and it's a bit shorter. So let's jump into a couple of the questions. I see one from Woong Jin Chun. For pipeline parallelism, how are transformer layers typically split across GPUs?
Let me switch to the Slack channel. Okay.
Yep.
Okay, I actually don't see the question here. So basically, I could give a brief answers. So the question is about how to split pipeline stages across transformer GPUs. So basically,
Yes.
um, it is only I think in the VLM frameworks it is by trying to split the actual transformer layers among the GPUs. So if we have like 28 transformer blocks, it is split among like seven workers. There will be like four transformer blocks per GPU, and from a transformer block per GPU, yes, and it will be sending the intermediate tensors from one stage to another. So and in that case, you have K values and V values. Um, yeah, that's the quick answer to that.
Good. And then we have one from Gaurav Kaul. Are the results purely from the analytical model, or was there a system simulator or tracing which was used? It looked like there was also, towards the end, you had some of the performance benchmarking results as well on actual hardware. But
Yes, we actually did no simulations, but we rather really care about when we are using the actual framework to deploy these models. So I think VLM is doing a great job in providing the observability APIs where we can grab towards when doing executions. Actually, it will actually have a internal graphing tool with the framework that it can spit out a histogram after each executions. And also with PyTorch profilers, it is also really insightful to use that to look at the GPU utilizations and also the number of calls, the number of tensor shapes that are actually getting transmitted during the execution. So yeah, these are the two main tools that we utilize to get our results.
And then just a couple more. We have one from Mikhail. How do you model communication and compute overlap? Or do you?
This in this paper we didn't because so for communication and computation overlap, one reason that we didn't model it a bit is because during with the recent rapid pace in the open source community, there's a lot of fused communication kernels that keeps popping up every other day. So it is really impossible to cover all the design principles in every choice design choices. And also, if you want to actually look at um, the overlapping ratio, it is actually achievable with the PyTorch profiler. So it will when you look at the actual trace, when you look at the timeline using the Perfetto online, you can also see the time spent during overlapping. Um, yeah, but we didn't cover it in this paper.
Okay. And then um, Wang Jin asks for end-to-end latency of tensor parallelism with 8 GPUs. Do you know the ratio of time between compute and communication?
Um, I think we did a small I will say let me check real quick. It was so I think we have like a we did a computation and communication split for 4 ranks within a node, but we didn't do it for across the node. So as we can see in the I can see in the slides that in the background session, which you can also say where you can also see I've already uploaded slides, but I think is around like more around 30% of the time is spent during computations and also around like 50 to 60% of the time during communications for tensor parallelism. So we did take some of the metrics, but we didn't take it for multi-node.
Okay. All right. Well, we'll have to end it there. Lots of interest. You'll see a few more questions in the chat. Just go to Hadi and look under the channels, and you'll see a day two channel there uh, f- uh, for the 10:30 time slot. Take a look. If others have questions, please dive right in. But Lang, thank you for a great presentation.